Hello, boys and girls. Welcome back to our study of electrochemistry. And the last part of this section we want to deal with is going to talk about the chemical industry, resources, needs, and chemical connections, where we apply electrochemistry at industrial scale. So, but in this content, we are going to deal with batteries, torches, and cars, how they actually work. So, you realize that the primary applications that make use of electrochemistry at industrial scale, it includes mining and mineral processing during purification of mineral ores, and also the electroplating and how we deal with rusting of metals. We deal with it every day in our households. If we pay attention, you understand that if you look at your table knives, forks, spoons, and other stuff, pots, they don't usually rust randomly because they are protected from rusting. And how they do that when they are making those utensils, it's an industrial operation that includes electroplating and protection of rusting of metals. And we can talk of chemical industry where we produce chemical energy, and that energy, that kind of energy sourcing comes more in the form of batteries. So we'll be looking at all these parameters and explain how do we come into all those as we do our writing of equations representing oxidation and reduction, half reactions, and redox reaction. So if you are wondering why are we emphasizing much about this electrochemistry section, if you look at our past paper, this is question 9, the last question, one of the last questions, second from last. See, this is also an electrochemical question, and see how many marks are 11. If you go to question 8, it's yet another electrochemistry question. And how many marks are there? That's 14 to make them 25. If you go to question 7, okay, this was equilibrium, but I'm saying in an exam of 150 and the 25 marks are coming from a single concept like electrochemistry or chemical equilibrium, it is very important for you to go into the exam when you are well prepared, when you are well equipped with background information that will help you to answer those questions as they come. Because as you can see here, those questions, they don't come asking common sense. They are asking technical things which you are supposed to know how to represent as you apply your knowledge, apply your skills and your technical know-how of interpreting the information, manipulating the data you get there through calculations, and be able to address typical examination questions. So, before we go into this question, I need to give you a quick background information of what exactly is happening here. If you check in our previous session, we were emphasizing more on galvanic cells. But remember, if you remember earlier on, we once distinguished that we've got galvanic cells and electrolytic cells or electrochemical cells. So what's the difference between the two? And if you remember very well, we said with the galvanic cell, the reactions are spontaneous. And those reactions, they actually generate energy or electricity. So meaning that we can actually source out electricity out of them. And we are saying your measure of the E cell will tell you whether you are going to have a reaction that is feasible or a reaction that cannot take place. And you can make those intelligent deductions from your representation of the cell reactions, half cell reactions and the overall cell reactions, and then you select the values from the reduction potential tables and do the manipulations to figure out is the reaction going to take place or not. So we identified the cathode, we identified the anode, and we identify the electrolytes in which the ions are there, where they facilitate the transport of electrons from the cathode to the anode, and then the electrons goes out through the external system from the anode to the cathode, and a completed circuit will ensure that everything keeps on moving like that. So this is why it is very important for us to now make a clear distinction of what is happening between galvanic cells and electrochemical cells. Okay. So just to give you a quick recap, we agree that the cell notation is a special format used to describe cells. Using this notation, the zinc copper cell known in, shown in 2.4 above, can be described as zinc, zinc 2 plus, and we agree that this single slash here, it represents the change in phase of material. So this is a solid changing into ions, and then this double hash, we agree that it's a bridge, it's a salt bridge which is separating two electrodes in the galvanic cell. And yet again here we are saying this is a phase change from ions to atomic copper. And we are saying that there is a simple way of interpreting this representation from the background knowledge that whatever you represent on your left is the anode, whatever you represent on your right is the cathode. Okay. So we are saying parts of the cell are written in sequence in which they appear in the diagram: the anode, the solution in contact with the anode, the salt bridge, and then the solution in contact with the cathode, and finally the cathode itself. So there are parameters that affect these cells, so like pressure and concentrations that can vary within the system. You can actually show how they change by putting those parameters in brackets. Okay. So we agree that the EMF of a cell, or the potential difference, is the difference between the electrode potentials of the two half cells. So that's why we said the overall cell potential is given by the the cathode minus the anode, where we are saying at the anode, at the cathode, oxidation is taking place, and then at the anode, reduction is taking place. So we are saying for the zinc copper cell, copper is the cathode, while zinc is the anode. And when we say E cell is equal to cathode minus anode, you will see that from the table of electrode potentials, the E cell of cathode is equal to 0.34, and that of the anode is minus 0.76. So for the overall cell, if you say 0.34 minus 0.76, it will give you 1.1 volts, which shows that this reaction can take place. Okay. So we are saying that if the cell potential is greater than 0, the reaction is spontaneous. But if the cell potential is less than 0, it means that the reaction cannot take place, or it's non-spontaneous. Okay, so now let's move on to electrolytic cells, where we are now talking of a completely different phenomenon other than the galvanic cells which we were explaining all along. So we are saying that in electrolytic cells, When electricity flows through a molten salt, now mark these words, when electricity flows, meaning that you are not generating the electricity. You are actually using the electricity from an electrical source, drive it through the electrolytic cell. So, in other words, we are saying the electrolytic cell, it consumes energy from an energy source. And you will see that the diagrammatic representation of an electrolytic cell is completely different from that one of a galvanic cell, because the galvanic cell actually produces electricity, but this one, it consumes electricity and uses the electricity to run it through its system. So we are saying when electricity flows through a molten salt or a solution containing ions or an electrolyte, the ions undergo a chemical reaction. So the process is called electrolysis, and it takes place in an electrolytic cell. So the reactions in an electrolytic cell are non-spontaneous and are sustained by the supply of electrical energy. So meaning that the moment you stop driving the electricity through the system, electrolysis stops. So an electrolytic cell converts electrical energy into chemical energy. Okay, but the opposite is true for a galvanic cell, where you actually use chemical energy to change it into electrical energy. Okay, so the electrolytic cell consists of two inert electrodes, such as graphite electrodes, these are carbon electrodes, which are connected to a direct current supply, such as a battery, and are placed into the electrolyte, and electrons flow from the negative terminal of a battery to the positive terminal through the electrolyte by negative ions and back to the battery. And during this process, we are saying the ions are undergoing chemical reaction. So what is important here is that how do you keep track of the chemical changes the ions are undergoing during the electrolysis process? So like always, we can keep track of such changes by writing down chemical equations where we account for the ions, the electrons which are being moved around, and the products which are formed. Are they kept in the system, or are they given off, or they go somewhere? That's what we need to be able to explain, and we see what happens with electrolytic cells. So here's an example where we are talking about electrolysis of copper chloride. We are saying copper chloride solution is blue in color, and when it is hydrated, we've got copper 2 plus ions in solution. So here we are, we've got copper chloride, put it in a solution, it gives you copper 2 plus ions and chloride ions. Okay, so look at the difference here. This is a electrolytic cell. So the difference of this electrolytic cell from the from that of a galvanic cell, this is the difference. The electrodes are not put in the same vessel. They are put in separate vessels. We can check the other representations we had in the morning of like this. It's more or less the same. Look at this real one like this. So you see that here, this is 1/2 cell, and if you take a look of the ions in this solution, this is copper sulfate, while in another setup, this is zinc sulfate. So the electrolytes are not the same. Look at the electrodes themselves. This is a copper electrode, this is a zinc electrode, okay? And you can actually see that the salt bridge has got a common ion. Here we are talking of a sulfate, and a sulfate also in the salt bridge. So my point I'm trying to drive home here is that, look, with a galvanic cell, the electrodes are not the same. The ions in the solution are not the same. And the setups are done in different vessels. But if you compare that to an electrolytic cell, everything is different. All the electrodes are the same. So like in this case, we are using an ion electrode. So if this is ion, this is also ion. And they are all put in the same vessel. And we use a common electrolyte. And above everything, we need a power source. Okay? We need a power source. So, in this particular case, we are saying our solvent is a copper chloride solution, or ions in solution, and our anode is positively charged, while our cathode is negatively charged. And we've got our battery over there, which is going to be the source of our electrons. So we are going to carry out this experiment in our next session as we answer typical examination questions. Okay. So what we are saying is that when positive and negative electrodes are dipped into the same solution, the copper ions, remember they are positively charged, and we said the anode is positively charged while the cathode is negatively charged. So what do you expect? Opposite charges attract each other. So the copper ions are going to move to the negatively charged species, to the negatively charged electrode, which is the cathode. Okay. And the half reaction that takes place at the cathode is such that when the copper electrodes reaches the cathode, they are going to pick up electrons. Then when they pick up the electrons, they change from ions to atomic copper particles. And how do we know that the copper is forming? So you see that if, let's say for example, if we are using carbon electrodes, carbon is black in color. And in this particular setup, we know that copper, atomic copper is brown in color. So if you see a brown layer or a reddish brown layer forming around the black carbon electrode of the cathode, then you automatically know that that's copper, which is being reduced at the cathode by means of picking up electrons, and they change from copper 2 plus ions to atomic copper solid particles. Okay. So the electrons are gained in this reduction half reaction, and hence the electrode is the cathode. So the blue color of the solution will start to disappear or diminish as more of the copper ions are getting out of the solution and depositing on the electrode of the cathode. And we are saying the reaction proceeds. Since the concentration of copper ions decreases, a layer of copper metal forms on the cathode. So what happens with the chloride ions? Remember, they are negatively charged, and we are saying the anode is positively charged. So we know that opposite charges attract each other, so automatically we expect the chloride ions to move or to be attracted towards the anode. And what do they do when they get there? We are saying the the anode is positively charged, and the chlorides are carrying an extra electron, which is making them negative. So when they get here, they lose the electron to the electrode. And then when they give up their electrode, their electron, they change from being ionic species in solution, and they turn into chlorine gas. So this is what happens. We are saying a balanced half equation of the oxidation process taking place at the anode electrode is such that two chloride ions are going to give up their electrons in an oxidative process and turn into chlorine gas molecules which will bubble out. We know a gas does not stay dissolved in a liquid, so that's why in this representation we can actually see that we have got some bubbles around the anode. It's because the chlorine ions are turning into chlorine gas, and it is those electrons they have given up onto the anode electrode which are carried back to the battery. So in other words, what we are saying is, while electrons are being discharged from this end, from the battery, going to the cathode and into the solution, at the anode, electrons are drawn out of the solution and taken back to the battery. So essentially we've got a complete circuit where we are going to keep on having a continuous flow of electrons until that point in time when we no longer have ions in the solution that will carry around the electrons. Then the whole electrolysis process terminates. Okay. So this is what we are saying. In other words, we can combine the half reactions and say that oxidation takes place at the anode and the net reaction is represented by copper chloride in aqueous solution to give us copper solid and chlorine gas. And the net reaction shows that using electricity or allowing electricity to flow through the solution of copper chloride ions, we can technically break down or decompose copper chloride by electrolysis process. Okay. So since the copper atoms are preferentially being deposited on the cathode, so we can actually manipulate electrolysis process and use it to decorate or to design or to transfer or to make specific materials according to our desires. Like in this case, an industrial application of this electrolysis is electroplating. So ladies and gentlemen, when I introduced this section, I told you that we use electrochemistry every day in our households. Take a look at your silver spoons, forks, knives, pots. Why they look silver the way they are is because they have been electroplated during an electrolysis process where silver was deposited on top of iron or cast iron so that you protect it against oxidation or rusting. So let's see how electrolysis comes to play during electroplating. So we are saying this is a process by which an object is coated on its surfaces by a metal of choice by an electrolytic process. So the object being coated here in this case, obviously you have to make it a what? A cathode, just like here where we saw that the copper was deposited on the cathode. So if you want to electroplate or coat a material with a metal of interest, you have to make that material a cathode in a electrolytic cell. So in this case, we have got this chromium anode, and we have got this material as a cathode, and in the solution we have chromium ions of 3+. So what exactly are we doing here? We are saying we are electroplating brass tapes with chromium. So this is brass. Brass, we know it's a mixture of copper and zinc. Okay, so we are saying the anode half reaction, this is the anode, copper, a solid, is dissolving, going into solution to give you copper 3 plus 3 electrons. And then on the cathode, which is our brass plate, we are using the cathode half reaction where the chromium 3 plus picks up the 3 electrons and form chromium atoms, and they will plate the brass plate. Okay. So we also use electrochemistry in processes of refining of minerals. One such application is in electro refining of copper. Okay, so that's why copper is very expensive. Is because they use a lot of electricity to purify it from its mineral ore. So copper is mined, or the mineral ore contains a lot of, or a mixture of other metals, silver, platinum, zinc, iron, and gold in various proportions. And they are in such trace quantities such that since we want copper, these small proportions of these other metals appear as impurities. So to remove those impurities, we reduce the conductivity of the copper and hence the need to refine it by an electrolytic process. So to improve the conductivity of copper, we need to remove all these impurities. So the impure copper acts as the anode. Why? Because it is going to dissolve and go into solution. And then when it moves to the negative, to the positively charged, to the cathode, they will pick up the electrons and become atoms. Okay. So we will get pure copper at the cathode. So this is what happens. At the anode, the copper goes into solution and forms copper 2 plus, and 2 electrons are carried through the external circuit from the anode to the battery. And from the battery, we do have an electric current which is flowing to the cathode. And to the cathode, the copper 2 plus ions will pick up 2 electrons and become copper atoms, a solid. Okay. In a similar manner, this process of electrochemistry is used for the extraction of aluminium. Okay. And that process is called the Hall-Héroult process. And we are saying here the aluminium oxide is separated from bauxite ore using sodium hydroxide. So in other words, we are saying the sodium hydroxide is going to be this electrolyte in which ions are going to be passing through. So aluminium hydroxide is dissolved in molten cryolite. Cryolite is sodium aluminium hexafluoride, which reduces the temperature of the aluminium oxide when it is electrolyzed. So aluminium is then extracted using electrolysis, and what we use as our electrodes, these are carbon electrodes. And all of them, they are acting as anodes. So where is our cathode? If all these are anode, so where is our cathode? Boys and girls, we are saying, when these carbon is used as anodes in a tank lined with carbon, which acts as the cathode. So you will see the internal lining in this container. This internal lining will act as the cathode. Okay. So let's take a closer look at this whole process. We are saying that this is a setup where we have got the steel tank with carbon lining acting as the cathode, and then we've got the carbon anodes which are inserted into the solution. And what do we have up there is a molten electrolyte of the mineral ore of aluminium oxide dissolved in cryolite. And then when this electricity is allowed to pass through it, the molten aluminium is collected at the bottom. And then the cryolite remains on top. So this is what is happening. We are saying that at the anode half reaction, the anode is here. Aluminium 3 plus, it picks up electrons and it goes into solution as a liquid. It melts and become a liquid. So when it melts and become a liquid, it sinks at the bottom of the tank. Okay, and then when it sinks at the bottom of the tank, at the cathode here, at the cathode, the oxygen 2 minus gives up the electrons to become oxygen gas, which bubbles out and leave 4 electrons. So where do those 4 electrons go? They go back up there. So we are saying the overall reaction is such that we have got aluminium oxide to give us liquid aluminium, and we give off oxygen as a gas. So aluminium the molten aluminium sinks to the bottom of the tank and is tapped off at intervals so that it does not fill up the tank. And oxygen reacts slowly with the carbon anodes to form carbon dioxide, and the anodes will eventually become smaller and smaller and smaller and disappear. So in the long run, they will have to be replaced. Okay. So why aluminium is very expensive is because aluminium extraction requires a lot of electrical energy for electrolysis, as well as keeping the materials in the molten state. So you have to keep on heating them sufficiently enough to remain molten. So, and the released carbon dioxide gives rise to greenhouse effect, and sulfur dioxide from the burning of coal give rise to acid rain, and coal is a non-renewable energy source. So you need to take note of that, as you might use it in some of your explanations as you'll be answering typical examination questions. One other application of electrolysis or electrolytic cells is the production of chlorine gas. Why do we need chlorine? Chlorine is used to make a lot of things. Industrial materials, all the plastics. If you remember in one of our sessions when we were talking about organic molecules, we talked about chlorination or halogenation of alkanes. So where is that chlorine? Where does it come from? We know that our oceans are rich with salt water. So salt water is called brine, and most of those salts are chloride salts. So if you take the brine solution, put it in a tank like this, and what you have is your anode. It can be a carbon rod which is acting as an anode, and yet another carbon rod acting as your cathode. So what you have, you'll have your brine solution or your salt solution coming in this way, and then when it comes in this way, the broken down or the spent brine will go out through that way. So what happens is that when the materials, when the solution comes onto the surface of the electrode, chlorine gas is bubbled out. How? I'm going to explain to you just now. And then on the other end, hydrogen is also given off as a gas, where you've got a sodium hydroxide solution which comes in there and goes that side. And this system is separated by a membrane like that. So let's explain this in details. We are saying what is happening at the anode half reaction, which produces the chlorine gas. We are saying we've got chloride ions. They give up their electrons to become chlorine gas, and 2 electrons are given off. And then at the cathode, we have got water, which is picking up 2 electrons, give away hydrogen as a gas, and form 2OH minus. So the overall reaction is such that 2 sodium chloride molecules will react with 2 water molecules to give us chlorine, hydrogen, and sodium hydroxide. And then we are saying the sodium ion is a spectator ion, and the membrane allows positive sodium ions to pass through it, while the negative chloride and hydroxide ions cannot. So it helps to balance up the ion gradient between the two sections of the electrolytic cell. So here is a comparison of the galvanic cell versus the electrolytic cell. This you must know, boys and girls. In an exam, they will ask you such kind of questions, and we are saying that galvanic cells have electrodes reactions that are self-sustaining because they produce their own energy, and we say that the reactions are spontaneous and are used to generate electric current, and they convert chemical energy into electrical energy. While electrolytic cell, they need external sources of energy to drive the electrons through the electrolyte, and they consume electrical energy, and they are used to break down compounds and other applications we've just explained right now. So a technical comparison of galvanic cells and electrolytic cells. First, I said by looking at the diagram, or where you are supposed to draw a diagram, you should know that with a galvanic cell, you have two separate vessels with two unique or separate electrolytes, and the electrodes themselves, they are not the same. So like for example, where I showed you earlier on, you could have a copper electrode as your cathode and a zinc electrode as an anode. And we are saying, yes, you have a salt bridge to complete the circuit, and you don't need a battery or a power source. But go to the electrolytic cell, everything becomes the opposite. You are using the same vessel, a common electrolyte, electrodes are put in the same solution, and you need a power source like a battery. So here we are saying in galvanic cells, the reactions are spontaneous redox reactions, while in the electrolytic cell, these are non-spontaneous redox reactions. And we are saying they produce, in galvanic cells, they produce electrical energy, while in electrolytic cells, they actually consume the electrical energy that has been produced. Okay. So the anode is the negative terminal, while in electrolytic cells, the anode is the positive terminal. And the E cell is positive for a galvanic cell, but E cell is negative for an electrolytic cell. And you see that with galvanic cells, we make a lot of stuff, electrical sources like torch cells, car batteries, and other materials. But while in electrolytic cells, we actually use the energy to carry out processes such as electroplating or production of chlorine gas. So you can actually see where we make batteries that things are looks completely different as compared to other, to the electrolytic cell. So where we make batteries, we can actually see that you have got your electrolyte solution like that, and then your anode and your cathode. And see the difference here. We are saying this is a lead storage battery. Most of the batteries you use in your cameras, in your cell phones, in whatnot, they are lead storage batteries. That's why you are able to charge them and use them, and then when they get used up, you recharge them again. So this is a simplified look into one of the batteries, and see how they make use of the electrolyte solution. And look at the anode, the lead, grid filled with sponge lead. So this one is filled with sponge lead, while the cathode is a lead filled with spongy lead oxide. So do you see that we've got two different electrolytes, sulfuric acid and lead oxide? Okay. If you take a look at another one here, this is a non-alkaline dry cell. We use these in our remote controls and other small gadgets. So you can actually see where the anode is. It's a zinc casing in an internal thing. And then the cathode is a graphite rod. And you've got a paste of the manganese dioxide in ammonium, chloride, and carbon. So that's why I've seen young people or even some old people, when the remote battery looks like it's no longer charging, they take it out and press it as if you are recharging it. Why you can actually press that metal casing and it collapses inside there, because inside here it's just a paste, not a solid material. Here's another mercury battery where we have got a paste of mercuric oxide, which is an oxidizing agent, and it's mixed in a basic medium of potassium hydroxide and zinc hydroxide. While the anode is this whole outside casing of zinc container with an insulation in between that does not, to make it less dangerous. Okay. You are expected to know how to explain in the account how fuel cells work. Like this is a common fuel cell where hydrogen comes in, you generate electricity like that, oxygen, and then you've got these two electrodes, you produce steam, and you generate electricity from a fuel cell. Okay. Boys and girls, I want to believe that with this, we cleared up a comparison of the galvanic cells and electrolytic cells, and where you are expected to answer typical examination questions where you show your understanding of these electrochemical principles and applications. You can make things work. So in our next presentation, we are actually going to carry out a small experiment where we show an electrolytic cell and possibly a galvanic cell, and then we answer question 9 of the 2018 May-June past paper. Thank you very much.